IP Tech Talk. Hello everyone and welcome to IP Tech Talk. Today we're going to discuss hybrid cables, which we use to connect access switches to APs on campus networks. We're familiar with both optical and electrical cables. Optical cables transmit data signals and, true to their name, electrical cables transmit electrical signals. Well, a hybrid cable is actually a combination of the two. This means that a hybrid cable can transmit both data and electrical signals. So, why do we need to integrate optical and electrical cables? And what problems do hybrid cables solve? This is a couple of the questions I'll answer in this video. As technologies develop, businesses are expanding their scope of their digital transformation, from the office to manufacturing and operations. In the process, the access layer on a campus network is becoming fully wireless. This is because companies need multifunctional and fully wireless networks that can quickly connect people, things, and environments anytime, anywhere. As we can see from this figure, fully wireless access needs cables between access switches and APs to be more robust. These cables need to transmit data very quickly and also provide PoE power supply over long distances. Conventional solutions use twisted pairs or optical fibers to meet these requirements. In this case, twisted pairs can transmit data signals while providing PoE power supply. However, their maximum cabling distance cannot exceed 100 meters. And in the case of optical fibers, it is true that they can transmit data signals faster at much longer distances, but they're made of glass fiber, which are insulators and cannot conduct electricity. This means that we need a local power supply for APs, which is expensive and difficult to manage. So, what's the solution? First, let's take a closer look at twisted pairs and optical fibers. Let's start with twisted pairs. Twisted pair cabling is a type of wiring where two copper conductors with coloured insulation are twisted together at a certain twisting density. Regulation on network integrated cabling states that the cabling distance of twisted pairs cannot exceed 90 meters and the total line length cannot exceed 100 meters. This is a huge limitation for wired Ethernet. But why does this happen? As I just mentioned, twisted pairs use copper wires as the transmission medium. This means that the transmission of network signals is affected by resistors and capacitors, causing attenuation and distortion. The attenuation is positively related to the cable length, so the longer cables lead to more signal attenuation. And once the attenuation or distortion reaches a certain degree, it affects transmission of signals. In addition, according to Maxwell's laws, an electric current produces a magnetic field. For twisted pairs, interference between magnetic fields is referred to as crosstalk. To avoid it, every two conductors are twisted counterclockwise. But this doesn't remove external electromagnetic waves. As such, when there is too much background noise, the bit error rate increases, which in turn severely impacts transmission. These are some of the challenges with twisted pairs. Now, let's move on to optical fibers. Let me illustrate the basic principles of optical fiber communication with an old experiment. In 1870, the British physicist John Tyndall conducted an experiment during a lecture at the Royal Institution. He drilled a hole in a bucket full of water and then shone a bright light into the bucket, as you can see in the figure. To the audience's surprise, illuminated water flowed out of the bucket hole, with light travelling along the curved path of the water stream. Why did this happen? How come did the light not travel along a straight path anymore? This experiment is an example of an optical phenomenon called total internal reflection. Water has a higher refractive index than air, or simply put, it's denser. So when light travels from water to air at an incidence angle above a certain degree, the refracted light actually disappears, or rather, is reflected back into the water. Visually, it's as if the light were bending through the water stream, as in John Tyndall's experiment. The concept of total internal reflection is the foundation for today's optical fibre communication. During signal transmission over optical fibres, we won't see energy loss due to the thermal effect of current or crosstalk caused by electromagnetic induction. What we do see are higher transmission distance and bandwidth. But is there any signal loss in optical fibre communication? Of course there is. There are two main reasons for this. One is absorption loss caused by absorption of light energy by fibre materials and impurities. And the other is scattering loss caused by light scattering outside of optical fibres. In 1966, Dr. Charles Quen Cao, known as the father of fibre optics, pointed out that optical fibres experience high losses from impurities in the glass, and not so much from problems with the technology itself. Dr. Cao predicted that optical fibres could meet the requirements of optical communication if we could just reduce impurities and therefore achieve glass light attenuation below 20 dB per kilometre. After many years of efforts, we know that this hypothesis was true. Scientists have invented glass fibres that are very transparent and fine, like a spider's web. These are the optical fibres we tend to see today, which are key to optical cables. Now, we've seen some background information on twisted pairs and optical fibres. Let's shift our focus back to hybrid cables. We know that both electrical cables and optical cables have some advantages and disadvantages. To recap, optical fibres support long distance and high bandwidth communication, but cannot provide PoE power supply. Electrical cables can provide PoE power supply, but the data transmission distance cannot exceed 100 meters. The obvious answer then is to design a cable that combines their respective advantages and addresses the challenges. And that's how we get hybrid cables. This figure shows what a hybrid cable looks like along with a cross-sectional diagram. As we can see, it is composed of optical fibres and copper cables. A hybrid cable has two types of connectors. There is the LC connector of optical fibres used for data transmission, and then there is the RJ45 connector of copper cables used to provide PoE power supply. You might be wondering, what is the maximum transmission distance that a hybrid cable supports? First, let's take a look at data signals. There is little attenuation since they are transmitted over optical fibres. So, the transmission distance can easily reach more than 10 kilometers or even dozens of kilometers. And how about electrical signals? Since copper cables only need to transmit DC electrical signals, the transmission distance can be quite long. According to Huawei's tests, hybrid cables can supply 60 watts PoE power even at a distance of 300 meters. That said, copper cables still have resistance and thermal effects still occurs during transmission, meaning there is some energy attenuation. Therefore, the transmission distance over copper cables is limited even for DC signals. Essentially, the transmission distance of a hybrid cable depends on the transmission distance of DC signals over copper cables. But as technologies and practices improve in the near future, we will see transmission distances reaching beyond 500 meters, which would meet the requirements of long-distance PoE power supply in most scenarios. With all this in mind, how can we build campus access networks that will still be relevant in the next decade? For this, in addition to hybrid cables, we need hybrid optical-electrical switches and Wi-Fi 6 APs. For example, we can use Huawei's S5732H switch, which is a hybrid optical-electrical switch. It supports a broad range of rates, including 100 megabit per second, 1000 megabit per second, 2.5 gigabit per second, 5 gigabit per second, and 10 gigabit per second, meeting bandwidth requirements in diverse scenarios. We can also use a hybrid cable to connect a hybrid optical-electrical switch to an AP like this. Such one-off investment paves the way for evolution over the next 10 years, even supporting the future Wi-Fi 7 with possible data rates of up to 25 gigabit per second. This prevents the need to recable and significantly reduces costs. Well, that brings us to the end of today's IP Tech Talk about hybrid cables. Thanks for watching and see you next time.